Because, you know, I'm not on the dating scene anymore, but it is nice to be physically healthy.
You should try the seafood diet.
Seafood needed?
Yeah. It works for me. I feel pretty sexy.
Yeah, your metabolism when you get turned my age, 40 years old, it really slows down, man. I used to eat way more than I do now, and I was skinnier. But I don't eat that much. I mean, I can't say I don't eat. I'm, you know, every now and then I get down, some barbecue. Can't, you know. Get down with some ribs. And this, I'm gonna keep this to 5 minutes because this really does. And the cool thing about this is like this leads into Einstein's relativity. Would you mind pulling down these stools and all that? So there's three things we're gonna look at here. Okay. Oh my goodness. Right when I was about to. Oh my goodness. You broke my flow, man. All right.
Go.
Okay. So if you have some coordinate system here, here's the origin. And you have another origin here, and you need to like talk. You can ask questions of me, but don't like interact with each other because it just drives me nuts. Yeah.
We do ice cream today.
Huh?
We do ice cream today.
No. Can I do my thing now?
Yeah.
All right.
You don't want me to
Okay.
Alright, we're good.
We're good. All right. So if I say say I have a vector going here, right? And I want to know what it is here. Do you see that a vector, if it's the same vector, and we're talking about relative to this coordinate system and relative to this coordinate system, they're going to be different. You see that? So what, can you think of the equation that we're going to do here? We'll call this, we'll call these vectors R. This will be our R here from this guy perspective. So this is R. Now from this guy's perspective, we'll call this observer prime. He's in this frame. Is it going to be shorter or longer?
Shorter.
Shorter, yeah. So then that means what we're adding to the original vector. Let me make sure I put these things on the right side. It looks like the difference between this here, we'll call this capital R. The difference between these two reference frames will subtract from this guy right here. Because these are both positive vectors, and this equals R prime. This is R prime. Do you see that it's shorter?
Yeah.
That's it. That's relative. That's all you're saying is relative from one frame to the other. It's just the subtraction problem of this position vector. Okay. Now, what if we're talking about velocities? So I'm going to go from here to here. Well, if we just take the time, if we just took the time derivative. Of course, you guys not in calculus yet, so we can't do time derivatives. But if we talked about delta r prime over delta t, delta r over delta t minus delta r over delta t. You see this is the same equation, just that now we have a before and after, we have some time taking place. So then we have v prime equals v minus, we'll call this capital V, which is just the motion of the two frames. So let's check out to see if this works. Okay, let's try it in a practical example. Let's see if this works. We have a choo-choo train going along in the positive direction. Okay, and it has a positive velocity, and we're the non-prime observer right here, right? And we see this ball rolling down the aisle of the train. How fast? And say this ball has, this is the train velocity. We'll call this capital V, because that's what I said here. That you guys are writing this down. You guys should be writing stuff down up here. I'm gonna get a drink of water while you get your picture. Good job for those of you who already have your paper out. You get a sticker. Not really, I don't have any stickers, but in my heart, I just gave you a sticker. We're seeing if my little derivation works here. Okay. So, all right, so the ball is rolling forward, and we call this velocity v. That's the velocity that we see the ball rolling in from the non-prime frame. That's us, here on the ground, not on the train. Now, if you have an observer, we'll call it the observer inside the train, observer prime, kind of like Optimus Prime. And he sees the ball rolling. Will he see it roll faster or slower than this guy here?
Slower.
Slower. So does this work?
Yes.
Yes.
Yes. Now if it's, let's see, if this velocity was actually slower, if he sees the velocity slower than the train, this guy would actually see it moving backwards. Like say if the train was moving faster than the ball, say the train's going like that, but the ball is not even keeping up with the train, it's going like this. This observer is actually going to see it roll backwards now. You see that? And that makes sense, because if the velocity of the ball is less than the velocity, let's see if I said that right. If the velocity of the ball is less than the velocity of displacement, then the observer prime is actually going to see a negative velocity. So does that make sense there too? Okay, then that works.
That would mean that the ball itself isn't going the same speed as the train. So it would have to be in the air.
No, it could be rolling backwards to this guy.
Oh.
Say it's rolling from the front of the train to the back of the train. He sees it as rolling in a negative vector, right? But because the train is moving so fast, this guy still sees it going in a positive direction, just not as fast as the train. Does that make sense?
Yeah.
Okay. Now, these equations work in 3D. I just did it. My thing right here is examples in just one dimension, but this works in 3 dimensions. And that's why I generalized with R. I didn't say X, Y, or Z, because remember R is like a vector in X, Y, Z space. Cartesian space, that's a fancy word for it. And then finally, what if you want to know the position as a function of time? Say the ball wasn't moving, but say the ball wasn't moving, and you want to know its position as a function of time. But the ball has a, let's see. Yeah, let's say the ball is not moving to observer prime. But is the ball moving to the original observer?
Yeah.
Yeah. Let me see if I'm thinking about this correctly so I don't screw this up. Usually put V prime over here. So V prime is going to be 0 though. And this, in our little example here, and this has to be, yes, I think we're okay. We're doing displacement. Yeah. Minus VT. So if, make sure I'm doing this right here. That'll be big V. And I'm not sure if that's a negative sign. Let's see. Yes, it works. Just check this out. If this guy is standing right here, if he say this is the 0, the origin on the train, the place where it starts, we're going to call that 0, right where the ball is, and the ball's not moving, but the train's moving forward. So our prime sees the ball as at 0, right? But we see its position vector growing with time, right? We see it displacing and it's getting bigger and bigger. But also, this thing is getting bigger and bigger at the same rate, but it has the opposite sign. It's a negative sign. So what's this still going to be as time goes on? 0. That's it. I'm done. Now acceleration, we're not going to worry about because if you're accelerating one of these frames, the physics is not the same anymore. You can't do Newton's laws, don't work. If the train was accelerating, like Newton's laws say that an object in rest does what?
Stays at rest.
Stays at rest. So if we have a pool table on the train, and I'll show you what I mean by this. There's a pool table on the train. If the train is moving at a constant velocity, will the ball stays at the same place on the train? So are they obeying Newton's laws? Yes. What if the train was accelerating? Then all of a sudden, magically, these balls start moving. Is that a violation of Newton's law? Yes, it is. It is for this frame of reference. But Newton makes an assumption that you're only talking about rest frames. The frame could be moving, but it can't be accelerating. Does that make sense?
Yes.
Okay. So hopefully I think I went longer than 5 minutes, but hopefully not too much longer. 13 minutes. Okay. I'm done.
Well, you weren't here.